Today we are going to do deleting from the LLRB tree, the left-leaning red-black tree. Now, this gets a little complicated. The removal algorithm is slightly more complicated than the insertion algorithm, but it's all, the way it works is, I think we can understand it. I think we'll be able to understand how it works, even though it is a bit complicated. Now, here are the steps of the remove operation. So this is the algorithm, and we're going to, by the time we get to the end of the hour, we will see the code, and we'll do a code walkthrough of the remove operation. All right, so here's the strategy. First, you find the node to remove. Second, you find the minimum of the right child of the node to remove, which is the successor node. Right? Third, you copy the data from the successor node to the remove, to the node to remove with the min operation, and that min operation is one of the methods that you need to code, and I'll give you some guidelines on how to do that here if you haven't done that yet. And then the last thing you do is you remove the minimum of the right child. All right? And then, so what we're going to start with now is we're going to look at the code bottom up. Okay? So so the first thing we're going to look at is removing the minimum of the right child. All right? So in other words, how do you remove the minimum of an arbitrary subtree? That's what we will address first. Okay? Now, and then here is a useful fact, and we mentioned this at the end of class last time, but check this out. The minimum of an LLRB tree has a nil left child. Now, why is that? Well, in any general search tree, binary search tree, now in a general binary search tree, you could have a situation like this. In a general binary search tree. And if you want to find the minimum value in the general binary search tree, the minimum is going to be less than the root. So it's got to be the left. It's got to be less than this. So you'd go to the left. It's got to be less than this. So you go here, right? And now, at this point, if this node, so you keep going left, and at this point, when you reach the minimum can't have a left child, because if it did, it wouldn't be the minimum. Now, is everybody clear on that? Okay. So the minimum of an LLRB tree, because LLRB tree is a search tree, is a binary search tree, it has a nil left child. Now here's another interesting point. The right child cannot be read, right? Because it's left leaning. So this link cannot be read because it's left leaning. So the only possibility for this is to be black. Are you with me? But look, if this is black, then this has to be nil. Now why is that? If this node is black, you can't have this in a left-leaning black tree. Why is that? That's because look, how do you count the black height? 1, 2, 3, and you skip any red ones, right? And so the black height of this, if it doesn't have a left, the black height of this node has to be what? What must the black, if these are all black links, what is the black height of this tree? The black height of this tree would have to be 1, 2, 3, and then one more to the node, that would be 4. So the black height of this node must be 1. But if the black height of this is 1, this must be nil, because if it weren't, it would be 1 plus the extra 1 at the nil at the bottom. So therefore, look, it has to be just like this, the minimum. It can't have a left child or a right child. It has to have a nil left child and a nil right child. Is everybody clear on that? Now see, this is really nice, because this means that because there's no tree hanging out here. See, ordinarily to remove this, we would have to do what? Ordinarily to delete the minimum, what would you have to do? Rem root. You know, and rem root, so you'd delete this, and this would have to come up to here. You know how we did that before, rem root? We don't need to do rem root. So we don't need a rem root. We can just simply do what? Just delete that. Now, does everybody see the logic there? Are you with me? Really nice, left-leaning. It eliminates all this other code that we would have to have? This restriction. Okay? Okay? So now, here is how, so now remember what we're doing is we are doing the last step of the general remove. We are deleting the minimum. Okay? So let's just assume for now that what we want to do is we have a general tree and we want to delete a general left-leaning red-black tree and we want to delete the minimum. So that's going to be one step in the final solution. So we're going to learn the code from the bottom up. So now here's the idea. You remember, why is it that when we inserted a node, what did we always make the parent link? When we inserted a node, what did we always make the parent link by default? Red. Now why is that? Because you wouldn't change the back height. So do you see that if we try to delete the minimum and the minimum has a red parent link, we can just delete it and not have to worry about the black height, changing the black height. The problem is the node to be deleted might have a black link to it. Okay, so here's the problem is the node to be deleted might have a black link to it. So here's what we do. The whole idea now is on the way down to find the node to delete, we create red links. Do you see what I mean? We actually create red links and we push these red links down on the way to the node to delete. And so finally when we get to the node to delete, we can guarantee that its parent is red, even though it might not have been red to start with. Now that's the idea. And we create these red links in such a way as to guarantee that when we fix them back up, the black height is maintained. The invariant is that the black height is maintained. Now, does everybody see the idea? You got to get that idea to understand how the code works. Okay? So what we do is we push red links down on the way to the minimum, which might create some right-leaning reds. But the thing of it is that our fix-up, you remember how the fix-up worked? From insertion? It's the same fix-up. We can fix those up on the way up. Are you with me? So now, once we understand the code for doing this, then everything else will make sense. So now we need some code to push those red links down. So we're going to have an operation called move red left. All right. The operation is called move red. You might have seen it in the code. There's a private method called move red left. And the purpose of the move red left operation is to push the red links down on the way to the minimum, so that when we actually see like if this is a minimum and it has a black link here, it's to push the red links down so that when we get to here, this will be converted to a red link. And once this is converted to a red link, we can just delete it. And then we fix up the right-leaning red links on the way up. Now, that's the idea. Now, this is a very common structure. In fact, we're going to see this in another data structure that we're going to do before the end of the semester. Okay? And the thing of it is that so we're going to look at how move red left works. And the way move red left works is it is only called on the way down if there are two left black links in a row. See, we're looking for the minimum. So if there's two black ones in a row, on the way down, that's when this gets called. Now, is everybody clear on that? That's just, we will say if, left is black and left, if not is red, left, and not is red, left. Okay? So those are the conditions under which it's going to get called. Okay, now, here is the code for remove min. All right, so let's just suppose that this is we have a tree and H is pointing to the root of some internal subtree. All right, and our precondition, the remove min, is not going to get called unless H is actually pointing to a node. All right, so the precondition is that H is not equal to null pointer. So we'll make sure that when we call remove min, that H is actually pointing to a node. And the post condition is that the minimum value is removed from root node H. So if, and you know there might be some other nodes down here, some of these might be red and some of these might be black, but the minimum is going to be here. This could be red or it could be black. And so, and if this is the minimum, then the post condition, so if we call it with H pointing to this node, the post condition is that a pointer to the root node of the modified tree is returned with this minimum gone. Does everybody see what that does? All right. Now watch how this works. Check this out. So you see the first if statement? If H arrow left equals null pointer. All right, so if H arrow left equals null pointer. And at this point, so right here, so here's H, so here is H like this. Okay, and if H arrow left equals, that means we finally got down to the minimum. Then at this point, because we've been pushing those reds down, we are guaranteed that this is, if this was not originally red, it is red now because we pushed it down. So you see, at this point, we are guaranteed to have a red link from the parent. Do you see what we're saying? And then what do? We delete H, and then we return null pointer. All right. So that and then that gets returned, and then there's fix up on the way back. Does everybody see that? So that's the first. That's what the first if statement does. And once we return, we don't need an else, right? Okay, and now what is this next part? If what? Not is red, H arrow left, and not is red what? H arrow left, arrow left. So that's, so now we're on our way to, you know, we're not at the minimum. So now we're on our way down. And what this is saying is if there's two what? Black left links in a row, what do? H gets what? So here we are, suppose H is up here. So H is up here. And we had two black ones in a row. Then what does it do? Then we do H gets, move red left H. So there is an adjustment that takes place at this point to create those reds so that we can push them down. Is everybody clear on that? That's the idea. All right? So that's called on the way. And maybe if there are two lefts in a row, then we just skip that one. Yeah, that's just, these are sequential ifs. Okay? And then, what's the last one? So now what's the last one? H arrow left gets what? So now you see, so here was our H. If we're starting up here, you know, on our way down, then you know it's like with insert, you know, H arrow left gets. So now this H gets what? And what do we call? Removement. But what's remove min? That's us. That's remove min. So do you see how it's removed? So it keeps calling on its way down. So everybody see how that works? I mean, what the idea there is. And then, one more point, what happens is, after H gets down there and it removes it, what does it do? Return what? Fix up H, but that's our old friend fix up. Boom, 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 boom. It's the same thing. So now that we know how fix up works, remember how that worked? There were three things, right? What was it? Yeah, rotate left, rotate right, stand up, sit down, five, fight. No, rotate left, rotate right, flip, possibly flip. Yeah, yeah. Okay. So that's the same one. So we're going to have to. So we will review how that works because that's going to enter in. Okay. So now here's the code for move red left. Now, the precondition for this is that H has a non-empty left and right. So whatever H is pointing to, it's got to have two, you know, nodes below. You know, the left child and the right child both have to be nodes, not nils. Okay, so that's a precondition. And the invariant is that either H or H arrow left is red. So, you know, one of these is, we're not going to call it if both of these are black. All right? And the post condition is a pointer to the root node of the modified tree is returned. So whatever the H is, we'll do that, it'll do that adjustment. Okay? And now let's take a look at, so you notice that it returns a node star. Okay, so it returns a pointer to a node, and move red left, and it's given a pointer, H is a pointer to a node. And let's take a look at the code, what this code does. First of all, move red left. The first thing that it does with no if statement, no ifs, ands, or buts, it flips the colors. Now, are you with me on that? The first thing it does is it flips the colors at H. Now, how did that flip colors work? Flip these, and it flipped this one going up, right? In fact, you coded that, or you will code that, right? So it flips the colors, and furthermore, maybe that's the only thing it does. Are you with me? Maybe that's the only thing it does. It does at least that. It might do that plus some more. Okay? So here's the thing. When does it have to do more? If is red, H arrow right, arrow left. So if we are here and it's H arrow right, arrow left, what happens is if this link is red, then it has to do a little bit more stuff. It has to do it's a little more complicated. If we are here and this link is red, then it has to do a little bit more. So what we're going to do is we're going to run through a scenario where the only thing it has to do is flip the colors, and we'll see how it all works. And then we'll do another example where it actually has to do that more complicated one. Okay? Is everybody clear? And then we'll see how the details of how that H arrow right gets rotate right, H arrow right, H gets rotate left, flip colors H. And then after it either flips the colors and does that, or just flips the colors, it returns H. So does everybody see it? And we'll see the details of why it does that and how it works in a minute. So now here comes our first scenario. We are going to delete the minimum, and I have set up this tree so that there's no red links to start with. Okay, so the only thing that the move red left is going to do is flip the colors. All right? So let's take a look. First of all, can we verify that it is a search tree? 80, 40, 90, less than, 40, 20, 60. Can you verify that's a search tree? Okay. And do you see that there's no red links there at all? And so the black heights all are common, right? The black height of 60. What's the black height of 60? Oh, by the way, I'm not showing the nils. You got to visualize that there's black links to the nils. So what's the black height of 60? 2. Right? Are you with me? It's 1, 2, to the extra nil at the bottom. Right? And what's the black height to 20? 2. And what's the black height to 40? 3. And the black height of 80? 4. Black height of 90 must be what? 3, which means the black height of L must be what? 2. Whatever, those are subtrees. Is everybody clear? And so those are bona fide red-black LLRB tree. All right? So this is the initial tree. All right? So now, let's go back to our code. What we're doing is we're deleting the min. So let's go back to our code. And so what does our code say for delete min? It says if H arrow left equals null pointer. That's not true, right? If is red H arrow left and is red H arrow left arrow left. H arrow left arrow left. So is that true? Is that true in part A of the figure? It's black from 80 to 40, and it's what? Black from what? 40 to 20. So that's true. Are you with me? So what gets called? Move red left. So what does move red left do? In this example, it only flips the colors. Why? Because the link from 90 to L is what? Is black. Are you with me? Now, does everybody see how that worked? So that only flips the colors, right? Now what happens? So that only flips the colors. Now let's go back to keep moving back to our code here. So we did that, and now what does it do? H gets what? H arrow what? Left gets remove min. H arrow left. So it's calling itself, and now with the new H where? Yes, to the left. So now it calls it with a new H to the left. But now look, can you see? Let's go back to part B. So you see when it goes down to, so that's going to, our new instance of H is going to be pointing to 40. Now does 40 have, now is move red left going to be called, yes or no? When it's pointing to 40. Yes, why? Because there's a black link from where to where? 40 to 20 and 20 to 10. So what's it going to do? The first thing move red left is going to do is flip colors. So what's that going to change? The links from 40 to 20 and 40 to 60 are going to turn from what? Black to red. And the link from 40 to 80 is going to turn to what?
Red to black.
Black. So now, are you with me on that? Yeah? So there we go. And now what happens? It's going to call, now can we remember the code now? What's it going to call? It's going to recursively call, and it's going to point to the 20. Now what about at 20? Well, wait a minute. From 20 to 10 is what? And from 10 to nil is what?
Black.
Now, is everybody clear on that? All right, so what's going to happen? It's going to flip colors at 20, but now what's that going to do?
It changes 40 to 20 to black.
20 to 10 will be turned to what? Red. 20 to 30 will be turned to red, and 20 to 40, the uplink 20 to 40 will be what? Okay, now does everybody see that that's part D of the figure? Yeah? Are we good? And now what's going to happen? Let's go back to the code. So now it's going to be pointing to the 10, which is on the lower left, right? And what does it say? What's the first thing it says? If what? On our code here for remove min. Equals no. What is it? Is it? Yeah, because that's nil. So it's a null pointer. So what does it do? Deletes H and what? Return null. And we don't have to do, notice we don't have to do what? Rem root. Right here is where we don't have to do rem root. Are you with me? See? Because there is no right child that we have to pull up. Yeah, because it's left leaning red black tree. Ah, this is, I'm going to show you how complicated it was before when we get to the end of this. Okay, so look. Oh, so do you see then that here it's going to point to 10, and then what's it going to do? Delete the minimum. And we are guaranteed that what? That the link to the parent was what?
Red.
Was red. See, so we're maintaining the black height. Now, are you with me on this? Okay, see how this all makes sense. And now what happens? The very last thing was what? Fix up. So it calls its fix up, and then when it returns to that, it will call its fix up. Now, do you remember how fix up worked? How is fix up going to work in going from, how are we going to fix up when the H pointing at 20? Do you remember what it checked?
Red.
A red what? A red right child. So what does it do there? It does a rotate left. And then if it had two what in a row? Two reds in a row, but does it? No. And then what?
A red left and a red right.
A red left and a red, but does it have a red left and a red? No. So what will that do? That will rotate, fix up with rotate left. Are you with me? Is this good? Okay, and now what?
And this one.
Now it's going to do, H is 40. Now how does fix up at 40 work? Well, red right child, so what?
Rotate.
Ooh. Now what? A rotate left. So where's the 60 going to go? To where the 40 is. Where's the 40 going to go? Down. Are you with me? And the left child of 60 is going to become the what? Come on, let's do the right. The left child of 60 is going to become the what? The left child of 60 is going to become the what?
The right child of 40.
The right child of 40. Now you guys remember the rotate? The left child of 60 is going to become the right child of 40. And that link is going to be changed from the what? That link is going to go, you know, it's going to be a left link. So now could you draw the next step? Could you draw the tree? Do you see that here in part G of the figure? That's what happened. Are we good? Let's follow this on through, all right? Are we good? And then what was the next one? If there's 2 red links in a row, but there's not. And what was the last one? Left and right are both red, but they're not. So now what do we do? That was the next one. Now how do we fix up the H pointing to 80?
Rotate left.
Rotate left, and no 2 reds in a row, and no left, right being red. So what does it look like? So where's the 90 going to go? Where the 80 was, and then where's the 80 going to go? Is the 80 going to go down? And what's going to happen? The what? The left child of 90 is going to become the what? Right child of 80. So look, boom. And there it is. And look, the black height is maintained. What is the black height of 90? 1, 2. What is the black height of 90? It's 3. What's the black height of 80? It's also 3. What's the black height of 60? 2. And what's the black height of 40? 2. What's the black height of 70? 1. Is everybody good? Okay. And what's the black height of 30? What's the black height of 50? 1. And what's the black height of 40? 2. Now do you see how the black height is maintained? Is everybody clear? Yeah? Now it's just slightly more complicated if that move red left has to do that intermediate code. So now I'm going to show you, let's do an example of that. So here's an example of deleting the minimum where move red left does more than just flipping the colors. All right? So check this out. So here we have H is pointing to 80. Let's verify that this is a search tree. 80 is less than 90, and furthermore 40, 20, 60, 10, 30, 50, 70, 45, and 55 are all less than 80, and 40 is greater than 20 and 10 and 30, and less than 60, and now, okay, are we good? That's a search tree. And what is the black height of 80? 4. What is the black height of 40? What is the black height of 60? What is the black height of 50? 2. What's the black height of 70? 1. But it's all, everything is consistent all the way down. Does everybody see how that? Are you with me on this? Okay, so now what happens? Oh, and by the way, notice that the what? That the link from 60 to 50 is red. Okay, so now let's start off at the beginning. So now, H now. H is pointing to 80. So now what happens? Okay, so yeah, here's the code for remove min. So if HR left equals 0 point, it's not that. So first we check to see if there's 2 red lefts, if there's 2 black lefts in a row. So let's go back to our figure. And there are 2 red, yes. And so if we look at our figure, there are 2 left black links in a row. There's a black link from 80 to 40, and then from 40 to 20. So what happens at 80? We flip colors, right? Are you with me? So in move red left, it actually flips the colors. So here in part B, it says move red left only flips the colors. Yeah? It only flips the colors. And now what happens? H goes down to the 40, right? But now what happens? So 40. Now are there two left blacks in a row at 40? Yes or no? Yes. From 40 to 20 is black. From 20 to 10 is black. All right. So now we're going to call move red left. But now what's the first thing that happens in move red left, what does it do? It flips the color. So what's that going to make happen? From 40 to 20 will become what? Red. From 40 to 60 will become, and from 40 to 80 will become black. Okay, so first, move red left flips the colors. Now, do you see that that's the deal? But now look, do you see now that, what did that do? Do you see why move red left has some work to do here? Because what did that create? Because the link from 60 to 50 was originally red, what did that flip colors do? It made what happen? Two reds in a row. Do you see? And we can't have two reds in a row. Are we good with this? So two reds, so how does it do it? Then those three statements inside that if of the move red left execute. Now watch this. So here's the, do you remember, I have it listed here on the caption, so we won't go back and look. But the first one was H arrow right gets rotate right, H arrow right. So what does that do? We do a rotate right at what node?
50.
No,
60.
it's at 60 because we're doing a rotate right at H arrow right. Now is everybody clear on that? Do you see what's going to happen? In going from C to D, what happens is we do a rotate right at 60. Is everybody? So how do you do a rotate right? What happens is, so the 60 is going to go what? It's going to go down, the 50 is going to go up, and now what happens? The right child of 50 becomes the what? The left child of 60. Are you with me? And then the 70 goes on down, okay, and the right child of 50 is the 55. So you see the 55 is hooked up to the 60, and the 45 comes up. And do you see that the black height is maintained? Are you with me? Okay, so now we're fixing that. So now we still have two reds in a row, but still it's a left and a left. And now the next statement in move red left is rotate left at H. So let's go back to our previous figure here. So now we're going to do a rotate left. Now do you see what happens if we do a rotate left at H? What's going to go down in part D of the figure? What's going to go down if we do a rotate left at H? 40 is going to go down to like where the 20 is, and the 20 is going to go on down with it, right? And now which child of which becomes the which child of which? The what child of what becomes the what child of what? Yes, the left child of 50 is going to become the what? Right child of 40. And then we will have two what? I mean, after we do that rotation, what will the links look like? Yeah, siblings. So you see here the 50 came up, the 40 went down, the 60 went, and so now the siblings, the 40 and the 60, have two red parent links. And so you can imagine what was the third statement in that move red left? Do you remember what it was? It was flip colors to fix that up. Okay, so look, boom, flip colors, and there we have it. And now we are at a point. Now we are at a point where we can do fix up on the way up. We'll fix it up. Do you see? So what we do is we set it so that fix up will work on the way up. This is so clever, and we can understand it all. I'll show you this code later on. It's a bear, the old code. Okay, and so now on the way down now. So when we go down, what do we look for? We're going to go down to the 40, and what's going to happen? What does it look for? Two black links in a row. And do we have two black links in a row? When we get to 40, do we have two black links in a row? And the answer is no. So move red left is not even called. And then what happens? We'll go down to the what? to the 20, and what happens? So we'll go down to the 20. Now, do we have 2 red blacks in a row when we're at 20? Yes, the black from 20 to 10, and the black from what? 10 to the left, nil. So move red left is called again, but this time it only flips the colors because the what? Because the left child of 30 to nil is black. Are you with me? So move red left only flips the colors. And so when it flips the colors, what happens? 1030. But now, you guys, we're at the bottom. And we are guaranteed that the what? What did we just guarantee? That the minimum has a what? Has a red link to the parent. So we can do what? Right off the bat. Just delete it. And we'd haven't affected the black height. So check this out. Delete the minimum. This is really slick. And so now how do we fix this up? Now can we fix this up on the, can you see it? Let's just do all 4 fix-ups. What's the first fix-up at H? The H is pointing to the 20. That'll be rotate left. And then what? I think there's nothing to fix up at the H at 40. And then what? Nothing to fix up at the 50. And then what? Flip at 80. So boom, after 4 fix-ups.
And it's okay that the parent link is red.
Oh, and yeah, now that is a very good point. Because the way all of this works is the red that goes up then is the part of the fix-up, because this is part of a fix-up. You see, so that red that goes up will be fixed up. You see how that works? The reason we use the fix-ups is because the reds propagate up, and so that's taken care of there. And that was a good point. In fact, probably on the slide it would have been better had I showed the red going up from the 80. But anyway, yeah. And if that were actually the root of the tree, that red would have been changed to black. Okay, so now we remove the minimum of the right. Now we see how to remove the minimum of the minimum of a subtree. So in the code, we're going to remove the minimum of the right child. Okay, so now let's think about how to copy the data from the successor to the node to remove with the min operation. So the code for the remove is going to call this min operation, and you're going to have to code that up. And let's take a look at that code and let me give you a little guidance here. So here's the min method, and the precondition is that h is not equal to the null pointer, and the minimum of the tree rooted at h is returned. So here, look, if this is h and this is the minimum, look, if this is h and this is the minimum, what does this function have to do? First of all, what type does it return? Does it return a pointer, yes or no? No, it returns what? A type T. Are you with me? So if this is h and this is the min, how are you going to program that up? Well, the precondition is that h is not equal to the null pointer, so you know that it's pointing to there's at least some data here, right? And I set up an internal local variable, p, which is a pointer to a node, and it's initialized to h arrow left, right? Are you with me? Now, so it's just one if statement and one while loop. And what's the if statement?
H does not equal null pointer.
Well, we know that the precondition is that h is not a null pointer. So what do we have to check? When?
Null pointer.
Yeah, what is the null?
The left child.
Yeah. The left child. The if statement checks to see if the left child is the null pointer. If the left child is the null pointer, we don't even have to do the loop. We can just do what? Return the data that h points to. Are you with me? Otherwise, what do we have to do? P has to go down what? Boom, 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 while, until it gets to this one, and then you return the data of this one. All right, so it's one if statement and one while loop. Okay, so you can code that up. And now Now let's think about the code for this. The remove operation, the whole thing. So now we've done remove the minimum of a subtree. We see how to copy the data. Now, and so what we have to do now is how do we do the code for the remove operation itself? Well, what we need to do is we need to look at the code for find the node to remove, and then find the minimum of the right child of the node to remove, which is the successor node. So here's the idea for the node to remove. See, now what we're going to do is we're going to start at the top of the tree, and we don't know if the node to be removed is the minimum. It might be where? Anywhere in the tree. Now, are you with me on that? It might be anywhere in the tree, but the strategy is the same. What we have to do is we want to make it, we want to keep propagating the what? The red links down till we get to the node to remove, and then propagate it down, boom. So, when we actually remove the min. Do you see what I'm saying? So now you see, it's the same strategy. We need to push the red links down on our way to find the node to remove. Are you with me? But the thing of it is that finding the node to remove may require moving to the what? Right, as well as to the left. Well, we saw how to push the red links down when we moved to the left. What did we have? We had this little auxiliary function that was called what? Move red left. But if we're going to, now we might have to move to the right to find the node to remove. So we're going to need a little auxiliary function called what? Move red right. It's just the mirror of the move red left. I mean, it does the same kind of processing as move red left. Same three lines, same flip colors, and if the condition is a little bit different, but the idea is the same. It's to make it so that you can fix it up on the way up. See? So if you move to the left on the way down to the node to remove, you call move red left as before. But if you move to the right, then we have this function called move red right. So here's the code for move red right. And so let's take a look at the individual parts of this code. Okay, so first of all, it will always call flip colors at H. So move red right might only flip the colors. But now here is what's different. This condition could not be repaired by fix up on the way back up. But now what is our condition? It's not if is, what was it before? If is red, it was left arrow right. Now what is it? Left arrow left. Why is that? Because we're calling this when we're doing what? Moving to the right. See? So it's if is red, H arrow left, arrow left. So it's if there's a red down here on the left, then we can't fix it on the way up because we're going to be coming up from the right. And so if there's a red one down there on the left, it couldn't be fixed up on the way up. You see, it's just a mirror. It's the same idea. And so we do this code. H gets rotate right H and flip colors. Okay? And I didn't make a figure for that one, but it's the same idea. You get the idea. Okay? And now here we go. Now we are ready to do remove. So here's the remove. So there's two versions of remove. The remove for the tree, and look what the remove for the tree does. In order for the node version of the remove operation to work correctly, it must assume, it has a precondition, that the data is actually contained in the tree. If the data is not contained in the tree and you try to do the node version of the remove operation, it breaks. And so the tree version of the remove operation first has to make a pass down the tree to make sure that the data that is being removed is actually contained. If it's not contained, then the root version is never executed. And then the root underscore root gets underscore root arrow remove underscore root comma data is the call to the node version to remove the data. And then the last statement is if there is an underscore root, if the tree is not empty, then we automatically set the color of the root node to black. And here is the code. if data is less than H arrow data. So what does that mean? This is a binary search tree, right? So we're going to move down to the left. Are you with me? And how do we move down to the left? The same way we did before, by removing the min. If is red, H arrow left, and is red, H arrow left. So 2 black links in a row on the way down. H gets moved red left, and then we finally go to the left. Are you with me? So that part's just like we did. Now, at the else part, what do we know? We know we either found it, or we're going to move down to the right. Are you with me? We either found it, or we're going to move to the right. That's what we know at this big else part. All right? So now, we have this first a little adjustment to do. We adjust the left link to, if there's a left link, we're going to be moving to the right. So if there's a red link to the left, we've got to make it to the right, so because we're moving to the right. You see how that, so we adjust the red link to the right, and we do a little rotate right now. And here, at this point, if data equals H arrow data, so we found it, right? But now under the circumstances where data equals H arrow data and H arrow right is equal to the null pointer, then what we have done is we have found it, and it is the minimum of the whole thing, and so we can return immediately. So you see we delete the node, and then we return null pointer. Okay? And here is our possible adjustment with move red right. You see, just the same way that we had to adjust with move red left when we were going down to the left. So it's the same thing. Only this time it's if is red, H arrow right, if is black, H arrow right, and black, H arrow right, arrow left. Okay, so that's the condition, that's the possible adjustment with move red right. And now here's the whole thing. So that's a possible, but now here, regardless of whether we do that or not, now we found the node to remove. Now check this out. Now we found the node to remove. So what do? H arrow data gets what? So that's copying the data up. You see, look, the minimum of what?
The right.
H arrow right. So it takes the minimum of the right. Okay? Are you with me? So it copies that data, so that's the one you're right, the min. So it will copy that into H arrow data. See how this is all easy to follow? And then what? H arrow right gets what? Remove min H arrow right, and that deletes the successor node. That's the one we just went through. Are you with me? Now that's if we found the data. If we didn't find the data and we moved to now what do we actually have to do? H arrow right, we recursively call remove. And then so we're going down, down, left, right, down, removing on the way down. And then what? The same, and then what? Oh, I should have put a thing in here. Return fix up. So it does returns fix up. Now here I want to show you something. I got to show you this before we leave. I'm sorry I'm keeping you a few minutes over, but look. This is the code for a general red-black tree, not left-leaning. And this is the fix-up for insert. And there's case 1, case 2, case 3, and then it says else, the same then clause with right. So there's a case 4, case 5, case 6. There are 6 cases, and look, there is a nested if inside of an if, inside of an else if, with a thing with case 2, and that might not, and not only that, it's all inside of a what? A while. And that's just for insert. That's 6 cases for insert, for fix-up. And look at this. Here's the remove fix-up. There are case 1, case 2, case 3, case 4, and then the same thing with right and left interchange. Case 5, case 6, case 7, case 8. And that's inside of a what? A while. With that complicated thing. And this is with parent links, and it's not recursive. And do you realize how many cases that is? That's 8 for this, 6 for the other one. That's what? 14 cases with the different fix-up. There's 14 cases for inserting the 14. And what is our fix-up? 3. I tell you, you guys, I saw that, kudos to Sedgwick, I saw that code, because this is what we used to have to do. And this is the way it is still done a lot. This left-leaning red-black tree thing is kind of a recent development, just a few years. Yeah. So anyway, so this might seem complicated, but man, it's nothing compared to the way it could be. All right, sorry to keep you over. Okay, we're going to conclude this video with a demo that shows a scenario where we do move red right on the way down to the node to delete. And the element that we're going to remove is 50. So here is a picture of the initial tree. Notice that it's rooted at 60, and 50 is to the right of 40. And notice that we cannot just go down to 50 and delete it, because if we delete it, it has a black link to its parent 40. So if we delete it, that will ruin the black height of the node at 40. So what we need is for 50 to have a red link to 40, so that when we delete it with a red link to its parent, the black height will be maintained. So the way we do that is we push the red link from 60 down to 50, so that 50 will have a red link to its parent when we delete it. So what's the first thing we do? Let's go see what the code is. So here we see when we first call the node version of removed, when we're at 60, if data is less than h arrow data, and it is, because the 50 is to the left of 60. So what is the if statement in this case? If we have two black lefts in a row, then we do h gets move red left, and then remove gets called recursively. So let's see what happens if we do move red left. So we are at 60 and we do move red left. Well, we've seen this code before. In this situation, move red left only flips the colors. So the link from 40 to 60, which was black, turns red, and the link from 80 to 60, which was also black, turns red, because those colors get flipped. And then it gets called recursively to 40. Okay, so now we are at 40, and it gets called recursively. So let's see in the code what happens there. Now notice that there is a black link from 40 to 30, a black from 40 to 50, and a red from 30 to 10. So here, data is not less than h arrow data, because the 50 is to the right of the 40. This is not true. It's not true that the left link of h is red, because we remember it was black, so that's not the case. The data is not equal. We're at 40, we're not at 50, so that's not the case. But here we have a possible adjustment with move red right. So this is the code that we'll trace. So notice it says if not is red, h arrow right. So if h arrow right is black and h arrow right arrow left is black, we do h gets move red right. So notice that we are at 40, and h arrow right is black, which is the link from 40 to 50, and h arrow right arrow left is black, which is the link from 50 to its left nil node. So that's black. So now here's where we do the move red right. So what happens with move red right? The first thing that happens is, so we're in move red right, the first thing that happens is we flip colors. So the link from 40 to 30, which was black, turns red. The link from 40 to 50, which was black, turns red. And the link from 60 to 40, which was red, turns black. The second thing that happens in move red right is rotate right. So when you do a rotate right at 30, what happens is the 30 goes up to where the 40 was. The 40 goes down and becomes the left child of 30. And the right child of 30, which was nil, becomes the left child of 40, which is now nil. So that's the rotate right. And now look what's happening. The 50 is getting a red link to its 40. And then the next thing that happens is flip colors. So we're flipping the colors at 30. So let's go back and see what that means. So if we flip the colors at 30, the link from 30 to 10 gets black. The link from 30 to 40 gets black. The link from 60 to 30 gets red. So there's 30 to 10 is black, 30 to 40 is black, 60 to 30 is red. And now when we call the node version of delete recursively twice, we get down to 50. And look, 50 now has a red link to its parent, 40, because that red link has been pushed down. So now we can remove it without changing the black height of the node at 40. And so the black height is maintained. And so after we remove that, boom, we can just do it simply with one just delete operation. And now when we return, we will do fix up at 40, we'll do fix up at 30, and we'll do fix up at 60. Well, the fix up at 40 needs no fix up, 30 needs no fix up. So when we fix up at 60, how do we fix up? Remember, there are 3 things to fix up. First, we do, in this particular case, it's going to be one of those situations where we do a rotate left and then we undo it with a rotate right in preparation for the flip colors. So first we'll fix up with rotate left. So the 80 comes up to where the 60 is. The 60 goes down. The 30 goes down with it. And now we have 2 red left links in a row. So we rotate right in preparation for the third operation. So there's the rotate right, so it undoes the first, the rotate left. And then the third thing is the flip colors. And then when we flip colors, boom, the link from 60 to 30 turns black, from 60 to 80 turns black. And then when we return to the tree version of remove, the parent from 6, the fictitious parent from 60 will be black. And that concludes the demo.